Hello, welcome! We decided to record an addendum to the first part for internal forces in beams. In this addendum, I will show you how to calculate the beam by writing equations once for the entire beam from the left side. And the second time, I will go through the same beam from the right side, and you will see that it doesn't matter whether we write these equations from the left or the right side. And for a longer beam, where we have 3 or 4 segments, or even 5, it is more convenient not to write all equations from the same side, but to write, say, 2 equations from the left and 1 from the right side. And just because I did that in the first part, for which I'm making an addendum, there was a question about why some force was not considered, specifically regarding the concentrated moment. Well, I explained that this moment was taken into account, if only in such a way that the moment applied affects the support reactions. So it is considered in the reactions, which in turn affects how the graphs look. So we can do it this way, that we do not reach a certain concentrated force or moment with our mental cross-section. We do not reach that force going twice from the left and once from the right or something like that, but it is still accounted for on the internal forces graph. So this video will show how to write graphs from one side and the other. I will show you the advantages of writing internal force functions once from one side and once from the other side of the beam. And I hope that it will clarify all doubts. So I have a beam here with continuous load, concentrated force, moment, and 2 supports. I also wanted to say that I won't be describing everything in detail here, because I described everything in detail in the previous video, in the first part. Here I will just show you that writing equations from the left side and then writing equations from the right side gives me the same result. So we need to calculate the reactions. I have marked HB and VB here. We know that from the sum of projections on the x-axis we can immediately calculate reaction HB, which is equal to 0. Then we can take the moment at point B. It should equal 0, so the resultant here from the continuous load is at the center of gravity. So since the entire load lies over a length of 6 meters, the resultant is in the middle, and its value is 10 times 6 meters, which is 60. And here we have minus 10 times 6, and now since the resultant is in the middle, we are at a distance of 1 meter from the support, from the point for which we calculate the moment. So minus 10 and it rotates counterclockwise, which means negatively. Minus 10 times 6 is the resultant times the arm of action of that resultant, plus 10 times 4. Minus 15, concentrated moment, minus reaction, Vd times 4 meters equals 0. From this, reaction Vd comes out as minus 8.75. So it came out negative. I changed the sign to positive. I underline it so I remember that I did this, and I changed the direction of reaction Vd to the opposite. I got a negative reaction, which means I incorrectly assumed the reaction's direction. Now we'll calculate the sum of the forces on the y-axis, which is 10 upward, minus 60 plus Vb, minus 8.75 equals 0. From this, the reaction V equals 58.75 kN. Let's do a check. As the sum of the moments at point A, right at the start of the beam, we have that 60 at 3 meters clockwise, so positively, which is 10 times 6 times 3, minus 58.75, meaning the reaction VIB times 4 meters, minus 15 plus 8.75 at 8 meters. And the left equals the right here, it adds up to 0. The left equals the right, meaning the sum of the moments equals 0, so the beam is in static equilibrium. And let's go. I will write the intervals. I'll create 3 intervals from the left side. The first interval, x1, is from 0 to 4. I won't be doing helper drawings here so that this video doesn't take too long. The shear force in this interval means cutting the beam in the interval from 0 to 4 meters. So the shear force in this interval equals 10 minus the resultant from the distributed load, meaning if we are at a length of x1, the resultant is minus 10 times x1. So if we substitute into the equation 0, it gives us 10, and if we put in 4, we get minus 30 kN. Let's calculate the moment. 10 times the arm x, 1 minus the resultant, which equals 10x1 at the arm of 1/2 x1. As I said, everything is detailed in part 1. So we substitute the ends of the intervals, which are 0 and 4. For the value of 0, we get a moment equal to 0, and for the value of 4, we get minus 40 kNm. Let's do the second interval, which is x2 from 4 to 6 meters. In this interval, we encounter one additional thing, which is the reaction Vb and Hb, but that equals 0, so we still do not see the entire distributed load, only part of it. So the equation will look similar. The shear force is 10 minus 10 times x2, and also plus the reaction Vb. So substituting 4 gives us 28.75. When we substitute 6, we get 8.75 kN. Now the moment. We have 10 at arm x, 2 minus 10 times x2, meaning the resultant from the distributed load, times 1/2 of x2, which is the arm of this resultant. And we also add the reaction Vb at arm x, 2 minus 4. So we substitute into this equation once 4 and once 6. We get minus 40 kNm and minus 2.5 kNmm. And the third interval, meaning we're looking from the left side from 6 to 8 meters. And I also had the moment at the end of the second interval in the previous video. That mental section BC is such a section that we are infinitely close to that point section C. And that moment 15 is exactly anchored at section C. And looking from the right side, if we make a section this way, we are infinitely close to section C. So at that moment, I did not reach that point from either side. Okay, section CD. So I am drawing, we cut the beam this way and cover everything that is on this side. We only see the left side. So we have, in terms of shear forces, we have 10 minus, we already see the entire load, so 10 times 6 and plus the reaction Vb. So we substitute 6 and 8. For the value of 6 and for the value of 8, it comes out the same, because this function is not dependent on the variable x. The moment in this section, CD equals 10 times x3, that is from this concentrated force of 10. Minus the entire continuous load. The resultant of the continuous load is 10 times 6, which is 60. And it acts on the arm, x3 minus 3 meters from the start of the beam. That is the arm of action. x3 minus 3. Additionally, we also have the moment from the reaction, Vb. So Vb acts on the arm x 3 minus 4 meters and moment 15, which is here. So minus 15, it is counterclockwise. That is negative. And to this long equation, because it's the third time from the left side. So we include all the forces here that were considered one by one, therefore it is worth making an equation from the right side. But I will soon show you what the equation would look like from the right side. So we have, if we substitute 6, we get minus 17.5 kN. If we substitute 8, we get 0 kNm. And we expected a value of 0 at the end of the beam, because there is no external moment transferred here. Okay, and now we will do the same, just doing these 3 sections from the right side. So I will rewrite all these equations on the next slide. And we have our beam. Also the reactions. I will highlight what was mentioned earlier, that the reaction V does not act this way but this way. And it is positive. Now with that, I will create section DC. And another extremely important thing. Because if we forget about it, many errors result from this. When making a cut from the right side, just as I will do now, positive shear forces are directed downwards. Positive normal forces are away from the section, and positive moments are counterclockwise moments. So it is exactly the opposite of the cut from the left side, and that left section is probably more intuitive because it is done more often. Hence, probably the errors arise if we start making sections from the right side. Okay, but we will calculate carefully here. So my section DC and this x1, let's say, is from 0 to 2, looking from the right side. So the shear force in this section is VD positive, because according to the direction that is positive for these forces from the section from the right side, this is a constant value of 8.75 kN. The moment is the force VD, which rotates clockwise, meaning this moment is a negative moment on arm x1. So I created this section that we are calculating now. So we substitute values 0 and 2 into the moment equation, and we get 0 and 17.5 kNms. And we can see that now this 0 is the 0 that we calculated here. And 17.5 is the 17.5 that we calculated from this equation. Now you can compare. Is it worth doing the third calculation from the left side and writing such a long equation where there is a high probability that we will make a mistake? Or is it better to at least once go from the right side and write an equation where we only see one force? And instead of such a long equation, we have a short one, and the result is the same. The effect is the same. This is the main reason why, when having a beam with 3 or more segments, it's worth writing at least one equation from the right side. I mean, not all from the same side, just at least do one from the other side. Segment CB, which is looking from the right side, from the 2nd to the 4th meter. The shear forces we see in this segment. I will also highlight this cross-section. The shear forces we see in this segment. I will also highlight this cross-section. The reaction VD, which is positive, and the resultant from the continuous load, which is also positive. And the resultant is 10 times the length of the beam on which it lies, and this length is x2 minus 2 meters. And substituting 2 and 4, I get the values. Now we can also compare what we calculated here for the 2nd meter and for the 4th. So it's as if we were here in segment BC. When we were in segment BC, we calculated for the 6th meter. The 2nd meter from the right side is the 6th meter from the left side. The value of the moment for the 6th meter was minus 2.5. The shear force is 8.75 for the 6th meter, which is 8.75 for our 2nd meter from the right side. As for point B, the 4th meter from the right side is the 4th meter from the left side, which is what we calculated here. And for the moment, here the equation is already longer. The reaction VD clockwise, meaning negative on arm x2, plus this moment 15, which we see is counterclockwise, thus in this section positive, minus the part you already know how to do, which is the resultant for the continuous load times the arm of action. And we substitute 2 and 4 into it, which are the ends of the segment. We get minus 2.5 and minus 40. Now let's do the third segment. Let's draw the mental cross-section we are considering. We are at this cross-section. We don't see that, we see everything that is on the right side. So the shear force VD is positive. The resultant for the continuous load is 10 times x3 minus 2, and minus V, which is directed upwards. So in this cross-section, it is negative. We substitute 4 and 8, which are the endpoints of the interval, and the result is minus 30 and 10, which is what we had from this side when counting. And the moment here is also a long equation. Minus 8.75, I was supposed to enter VD here. This is the reaction on arm x3, join plus 15 moment, minus the resultant for the continuous load times the arm of action of this resultant. And to that, also plus the reaction VB, which rotates counterclockwise, so in this cross-section it is positive times the arm of action, which is x3 minus 4 meters. And again, we can compare this equation, and the effects, the numbers we get from it, are the same numbers we get from this equation. Here there is not such a big contrast, although there is still some. But you can compare and assess that it is worth not writing the internal force functions continuously from one side. And we also substitute extreme values into this equation, that is 4 and 8, and we have results. It turns out that at the 8th meter there is a zero moment. This is also a good check of this last equation. If we know that at the end of the beam it should be 0, then when we substitute into this equation the end of the beam, looking from the right side at coordinate 8, it should yield 0. If it does not yield 0, we can be sure that this equation is written incorrectly. So this is also a good check. And I hope that with this comparison I have encouraged you and convinced you to lean towards writing at least one equation from the other side. Rather than trudging through these force functions only from the left side, because we are adding more and more forces, these equations are getting longer, and it is easier to make a mistake. Now we are rewriting those forces that we obtained for individual intervals. And as I said, this video is not here to explain to you how to draw graphs, because previous courses covered that. So I will just display to you how the graphs should look. As you can see here, you would realize that there should be an extremum. You know how to calculate it from previous courses. So try to go through these graphs on your own and understand why they look that way. And that's it. I hope you managed to understand even more thanks to this video. I greet you. Take care. Goodbye.